I opened the issue of neutrino mass, right? Maybe for us, for you especially here, for me for personal reasons, but for you coming out, maybe the sort of most exciting aspect of the Standard Model, because this is the only place where it failed. Standard Model, after all, if you think about it, I've already been giving you a glimpse of how successful it is. It works to 1 in 1,000 in many of the cosmological aspects, predicted from the very beginning theoretically, in weak interactions. And even beyond that, in a sense, because by trying to understand weak interactions and make it normalizable, the theory, so that we can compute, we ended up with a mechanism that gives us the origin of particle masses. So we went much more beyond. But deep down, the theory that we call the Standard Model, Standard Model in name is sort of not so nice, okay? Frank Wilczek writes popular books. One of the fathers of the physics of the Standard Model, he calls it the core theory. And it's kind of nice because Standard Model, it seems, there are many models, and you just pick up a model which you like more and became a Standard Model, right? It's a deep, profound theory. And it's a fundamental theory of all the particle interactions. But the electroweak part that we are talking about here, it studied as a theory of weak interactions. That's what we wanted to do. And we were a little bit more ambitious, wanted to be able to, or they were, make precise computations. And the weak interactions is all about the main protagonist, in a sense, is neutrino, right? I mean, that's what sort of opened the window to new physics, okay? This missing link when the first weak interaction neutron decays was observed. And neutrino standard Model makes a beautiful prediction, very clear, that neutrino is massless. Whereas the other masses, we cannot predict the number for neutrino, we can, it's 0, okay? Unfortunately, failed. So I was trying to argue in the last lecture that it's very natural from various points of view, and I've been carrying it along, that neutrino actually is a Majorana particle. I couldn't prove to you that it has a mass. That came from outside, right? In the Standard Model, neutrino was massless. But once neutrino has a mass, I try to argue, I hope this you notice, I can't prove that, but it's very likely it's a Majorana particle. I don't know why. I offered a few arguments. So the first thing we did, we said, well, if it's massive, let's do the usual change. And then the right-handed particle, okay, that's the most natural thing to do because other fermions has right-handed counterparts. So we said, okay, if I add a right-handed neutrino, and I write the more general Lagrangian for neutrino, it turned out that there was something that I call the Dirac master, LL bar. So in other words, there is a doublet, nu L bar, and the right-handed neutrino. There is, of course, right-handed electron at the moment. It's not so important. Then we said here there was phi tilde and nu R. And we realized that there was actually a very important additional term we could write, because right-handed neutrino is a singlet, carries no gauge numbers, okay. The more general Lagrangian actually has this form. Now notice the name, okay, the name of right-handed neutrino is a little misleading, okay, because it's not really a neutrino we ended up deciding, it's more likely a heavy particle. We call it right-handed because this is the guy they couple to induce cover interaction with the right-handed helicity, okay. This of course produced immediately Yukawa Dirac V over square root of 2, which I called M Dirac, master mu L nu R. And then I have this thing. Now, although I have no idea what the mass of the right-handed neutrino is, okay, I try to argue, and this is the usual argument that is offered in textbooks, that having the origin outside of the standard model, okay, has nothing to do with the symmetry breaking of the standard model. You see, the scale of the standard model is the scale of the vacuum excitation value. And in case of fermion, often suppressed by small Yukawa coupling. Whereas the U scales, we expect them to be above the scale of the standard model. In that kind of picture, if it's true, then we would notice immediately this is not a neutrino, right? It's a heavy lepton, okay? And it's a particle by itself, which mixes a little bit with our particle. Notice the other day I introduced immediately Majorana spinor out of nu L and nu R, which is one convenient way of dealing with sort of a funny mixture of Dirac and Majorana. It's a little complicated to know how to deal. But notice that even before that, I mean, I have here mass matrix, but in order to deal with it, ideally would be to have one and the same notation, either Dirac or Majorana. Okay. Notice that I can always rewrite that in the Majorana notation. Okay, this is Dirac. Now why? Recall that every particle, when you have a particle, even if it's just a left-handed particle, but every spinor has an associated charge conjugate spinor. And it's equivalent to work with a spinor or its charge conjugate. After all, I don't know who is more basic, right? The size C is psi. So you can also say that our spinor is a charge conjugate of that spinor, okay? You can work with the electron or the positron, depends what you like to do, okay? So in other words, if I have a left-handed spinor, this goes into, we decided, a right-handed anti-spinor, because we found out that when I perform this charge conjugation, I change parameter. In the case of massless particle, it will be changed because therefore, well, I meant I can work with a left-handed neutrino or a right-handed anti-neutrino. There is always another state, but it's an anti-particle, okay? So the reason we speak of a left-handed neutrino in the standard model is because this is the way the neutrino that we like and cherish couples to the electron in the W boson. Okay, here is the name. Nu L bar, gamma mu EL, W mu plus. This is why I call it a left-handed neutrino, because it interacts with the electron with a left-handed component. But if there is a left-handed neutrino, there is also a right-handed anti-neutrino. Okay, just to remember. In other words, I could work with nu CR, which would be C nu L bar transpose. By definition, this is just a name, okay? I hope it's not confusing. So if I take a transpose of this, what would I get? I take a transpose, I will get this. Okay, the privilege of the blackboard, okay? You should check it if you're writing while I'm doing it. You agree? In other words, I know immediately that nu L bar is now is nu C. I put this R just to remind us, transpose times C. It's good to remind us that CT actually is minus C, and C square is minus 1, if you remember. We had our, check it with our conventions, I gamma 2, gamma 0, but this is a generic property. Therefore, when I multiply it by the inverse, that's C. So this is true. No. Why don't I do the other way around? Sorry. This is better, right? I multiply this relation with C. And I use the fact that CTC is 1. Well, that, you know, you always keep that implicitly when you speak, when we spoke of physical processes, we said the particle entering, it's antiparticle going out, right? We always had that in mind. Okay, this is what it means. Okay, the particle going out, this is the particle going out, U bar, is antiparticle entering, you see. This is physically what it means in this notation. The only thing to remember that there is a charge conjugation to put there. So in other words, this Dirac mass term, I could always rewrite is nu C R bar transpose, C nu R. I can always work with my Majorana notation. I don't have ever to introduce a Dirac notation. I will introduce Dirac particles when the particles carry charge, because I'll get both different choralities. And actually, this, by the way, this would be important to learn if you go into physics beyond the standard model, almost any direction that you want to do, whether it's supersymmetry if you like it, that may take you to superstring, or whether you like grand unification. You know, in grand unification, what you like to do, you like to unify weak and strong interactions. Therefore, you put particles together, like quarks and leptons. So typically what you end up in a theory like grand unify, okay, a side comment is that you're going to put both the doublets and the singlets together. Imagine that you like a theory based on SU5 for some reason. Let's imagine. Okay. Prototype. A digression, not a moment to learn. Okay. In the last lecture of the course, I will definitely come back to it. But just imagine for fun that you want to do that. Then you would say, oh, I will put my fermions in a minimal representation. I always start like that. This is, you know, when you're going out, you know, well, Goran taught us, okay, in the standard model we took a doublet. In the SU3 theory, I would take a triplet. This is how I'm going to start and see where it takes me. That's the easiest thing to do, okay? Always try the smallest group and the smallest representation, see where it takes you. Okay, so imagine that I take a fundamental or for fundamental or for fermions or whatever. So it's and I say the following, okay? The first three will be color. By the way, in the SU5 example of symmetry breaking, the first three I call SU3, and the second two components I call SU5. Here would be actually the physical color, and here would be, in other words, SU3, and here would be SU2. This is grand unification. What he wants to do was to unify color with chiral electroweak interaction, okay? So there will be a doublet here. So what should I, and has to be a singlet under color. So which fermions would you put here? Suppose this is the night 1974, you are Georgia and Glacier, and you are just realize that you could maybe try to do that, okay? See how it will go, just to give you a feel. What would you put here?
Electrons and neutrinos.
Neutrino, very good. You will put nu and e.
Yes.
And it will be left-handed.
Yes.
Okay. Now here I have to put quarks. By the way, has to be the same quark, because the color doesn't change flavor. Okay. So it's some quark coming in three different colors: yellow, red, and blue, say. And it has to be a singlet under, but left-handed. Then you say, oh, what to do? But only the right-handed quarks are singlets. Okay? This is the first moment when you have to think a little bit. Right? We wrote the standard model with UDL, UR, DR. Important lesson on what I've been stressing all the time, but it sort of tends to escape. So remember, I can't put the right-handed guy here because then I would break Lorentz symmetry. See, SU5 takes any particle to any particle here, okay? You cannot break Lorentz symmetry. I don't want to take left to right by performing an Italian transformation. In other words, my group here, when I say it's SU5, it's Gat times Lorentz, direct product. Otherwise, all hell breaks loose. So So that means that this particle must be left-handed and must be a singlet. So what should it be? I go there. It's one of the two guys, but they're right-handed. How do I make them left-handed? Work with an antiparticle. Because it said there is no difference between particle and antiparticle. When there is a particle, Dirac teaches you there is an antiparticle. And what you call a particle is just a convention. Simply, nothing more than that. So instead of this, I could work. So why not I write here? Instead of UR, I could work with UC. Remember, which is left-handed, because that's, by definition, CUR bar transpose. And in the process, I change the chirality. Or I could work with D, R becoming DC, L. Which one would you put? How would I decide? Okay, this is not neither the time nor place to teach it, because we understand the model, but you see how I can't help myself to teach you what I would really love to teach, and that's the physics beyond the standard model, which I do for my living. But anyway, notice that if I say that the theory is whatever I say it is, that means that electromagnetic charge, and I gave you a homework problem that I said, look, one day you may end up with a complicated theory which are a bunch of fields. You have to find the charge and the photon. By definition, the charge must lie inside the group. You agree? In other words, the charge is some combination with some coefficient over the generators of that group. I don't know which one, I don't care. What I know is that the generators are traceless and Hermitian matrices. Therefore, what I prove immediately that trace Q is 0. So in other words, charge is not arbitrary anymore. By the way, this is the reason, maybe the deepest reason why so many of us love grand unification. It automatically explains the magic of charge quantization. It's not arbitrary anymore, because it must sum to 0. In the standard model, it was arbitrary. I had no idea what this charge was. It was a singlet.
Can you repeat the part of the charge?
I said charge lives in a group, so it's some linear combination of the generators of the group. They are traceless. Any SUN theory will give me. It doesn't matter it's SU5. Maybe you don't like SU5. You said, I like better SU7 or SU125. I don't care. I said trace of Q would be 0.
This charge is electric charge?
Yeah, of course. We're talking about. When I say word charge and I don't specify it's electric charge. Once you know that, tell me which quark should I put there. This is now not so important. This was important to teach you, that to give you the lesson of the notation that you can always go into the Majorana picture in which you work with the same chirality if you wish. Which quark should be here?
Positive charge?
What is the charge here? -1? 0? So this must sum to 1. That means each of them must carry 1/3. Because color is a good symmetry, they have the same charge. So which guy is here? This or this? Down. Okay, I even predict the structure, okay, and I predict charge quantization. So this was just an example here. We'll come back to it. This is a fascinating subject. By the way, one other side remark I can't help making. I told you that there was one way of understanding charge quantization due to Dirac. And that was the following. Dirac, in 1948, I think, writes the following paper. He says, imagine that there are magnetic monopoles. Wouldn't the world look more beautiful, more symmetric? Right? You will have the duality symmetry between electric and magnetic field. In other words, that besides the charge, electric charge, there is also a magnetic charge, the form of magnetic monopoles. Many people thought of this before. He took it seriously and he constructed a quantum mechanical theory of electron, say, and the magnetic monopole. He found out that the product of these two quantities, whatever charged particle you take, must be proportional to integer. It's worth knowing this. It's very hard to understand how this works. It's a beautiful subject. In other words, charge would be quantized. One monopole would be nothing. One bloody monopole. Only have to find one monopole, okay? And they would explain charge quantization, okay? What happens is that in such a theory like this one, you predict that magnetic monopoles must exist. This is really beautiful. Not that you assume that they may exist and give you charge quantization, because here charge quantization is built in. You actually predict the existence of magnetic monopole. But this is taking me away from my duty. This is like doing homeworks, you know. Notice often when you have to do homeworks, you rather do other things, you know, go jogging or whatever, you know, do the things that you like to do, especially if it's the homework that you didn't want to do it, okay? So the lesson here was that I can always rewrite whatever I write in the particle form in terms of the antiparticle. Therefore, if I had a Dirac mass term, it will look like Majorana. It will look like, it's not Majorana. You see, Majorana mass term is when you have the same particle. This is called Majorana mass term. Majorana mass term breaks any quantum number associated with this particle. By the way, since it is a singlet I'm breaking, no gauge charges here, right? They're all conserved in this particular example here. But if this guy carries some other number, and by the way, by coupling it like this, notice I define the lepton number of noir. Neutrino is a lepton, therefore noir is a lepton. Okay, this carries lepton number 0. That's how I define it. So this is a lepton, this breaks lepton number. This is not a Majorana mass term, it just looks like. This is a Dirac mass term because this is a lepton, this is an anti-lepton, okay? Please notice. Yes. This is just a Majorana notation. But it is a Dirac mass term. Here lepton number is broken, here lepton number is good. The reason I'm telling you, you can immediately then notice that we have a non-trivial mass matrix. You don't have to introduce the Majorana spinors to start with. And by the way, when there are more generations, this may be more useful, okay? We'll have to generalize it until you see who is the particle and who is the linear combination of particles and whatnot. Okay. So, this is what we did last time. In other words, the mass matrix between nu C right-handed and nu right-handed will have this form. I decided to call this Mn. Less indices. And this is where we were. Remember, this is my neutrino, just written in a funny form. This is neutrino, this is nothing to do with the right-handed neutrino. This is a left-handed neutrino. Or if you wish, it's body, it's anti-body, which is there. And we concluded here, okay, see this was the first argument that if Mn is much bigger than M Dirac, if, and actually the logical assumption we said would be that Mn is actually much bigger than Mw. It's coming from a new physics, presumably. It's a gauge singlet. It has nothing to do with the standard model, strictly speaking. Then we found the eigenvalues immediately. What were they? Well, obviously one is Mn, because this is very tiny. So we call it M heavy. And the other is m light is minus m Dirac squared over mm. Remember, I never worried about the sign of the Fermion mass when we talked about Dirac particles. It was irrelevant. I could change it by changing the, say, right-handing component. But in the case of a Majorana guy, one has to think a little bit because the sign may be important. You can get rid of it eventually, but that means redefining the field itself, the field that you have under in your physics. Okay. So let's keep it. And that we said, in other words, that means that nu R is actually some heavy lepton, heavy neutral lepton. And it has a Majorana mass term, therefore it is natural to introduce n, which is nu R, plus C nu R transpose. You see what Majorana does. For every particle we said there is an antiparticle that exists by definition, okay? Majorana just says I can put them together in one and the same state. Okay? This is what Dirac overlooked. He was not worried about charged particles. But he was worried about the structure of the Dirac-Lagrangian Dirac equation. It was simply overlooked by everybody, okay, for some 10 years, that the Dirac-Lagrangian allows for this possibility. In other words, the generalization of it, if you wish. But this is a landmark moment, 1937. By the way, this guy, you know, there was this great school that Fermi created at a small institute in Via Panisperna in Rome. It's a not big distance from the center, so if anything takes you to Rome. I don't remember the number, I think it was 7, but you should check it, I'm not sure. Okay, I may be wrong. Okay, so there were this bunch of young, brilliant guys who were, you know, equivalent of doing PhD. And they got to know a fellow who was an undergraduate student by name of Ettore Majorana. And it took you about 5 minutes to realize that there was something unusual about this young man. Okay, he was in another world. So they take him to Fermi to show this. He was very shy, very isolated person. So he goes to Fermi, this very shy guy. And Fermi is already one of the leading physicists of Europe. So Majorana asked him what he was working on. It's a big thing, you know, they take you, you know, you go and you meet Feynman, you say, okay, Mr. Feynman, what are you working on? Okay. So he was working on what was called the Fermi-Thomas statistical theory of nuclei. He was working for 6 months. And he's thinking whether he should explain this to this young guy, you know, it's, why should you explain that to the student? Okay, well, he says a few words, but this guy understands and asks a question. And so he says a little more. And there's another question, and he sort of tells him what he's doing. He's puzzled. Okay? He's never seen anything like this before. This was in the afternoon. The next morning, comes Majorana. He has a piece of paper. Works on the office. He says, please can we check? In doing this, he was doing this for 6 months. Now, I don't know if you know, but Fermi was famous not just of being a great physicist, but being one of the best calculators.
Yes.
Of that era. You know, if you were there, one of the things he would have a competition with you on the blackboard, who is going to be faster, okay? It wasn't enough to be great. He had to be faster than you. And he was. So he worked for 6 months. The guy says, can we check please something? Do you get this result, no? Fermi goes, looks at the manuscript, he doesn't remember. He says, oh, yes, I did, you know, now he doesn't understand what's going on. And this? Yes. And this? There are about 5 or 6 results. Then Majorana says, ah, good, he says, then I think you're right. He didn't say, I think I'm right. What he did at night, he solved the problem exactly. He reduced it to some other thing, to some other thing, and some other thing. And of course, Fermi was to witness. Apparently to him, an unparalleled genius. He says something like this, Fermi, that, you know, there are physicists that do good work, important work, special work. You could even say maybe outstanding physicists, but they end up in the dustbin of history, typical. And then there are great physicists, he says. Heisenberg, put some names, I don't remember precisely. And then there are geniuses, he says, like Newton, say, which you and I cannot comprehend. He says, to me, Ettore Majorana was above any of them. He just lacked common sense. Ettore Majorana wouldn't publish. It was hard to get him to publish. It seems that it was so easy to see whatever he was doing. So it would look like this. I just have to tell you the story, it's amusing. Okay. I'm fascinated by this guy. They're having lunch, typically what will happen there. They're having lunch. And there is a discussion of some new physics, okay? And one lunch they are finding out that Irena and Joliot-Curie have some new results that cannot be comprehended. This is 1930. And there is no neutron in 1930. I don't know if you know that. 1932, neutron is discovered by Chadwick. So they have this puzzling result, and this is just a lunch. And he comes, you know, has a look, and he has this funny way of speaking. If you were not quick on your feet, if you didn't understand something, he would call you, it's not a good word in Italian, stronzo. It's like okay, I'll just say, you're really dumb, he would say. He says, oh, but these idiots, let's say, these morons, I don't understand, it's obvious, he says. Obviously, besides proton, there is a neutron which has the same mass, and it's neutral, this explains everything. You know, your first reaction, here comes a guy, tells you that, you're a little sort of unnerved. But as the time goes on in the afternoon, Fermi realizes more and more that it seems that he's right. That means Nobel Prize, you understand. He's predicting the existence of a new particle that, of course, will shake physics, change nuclear physics forever. When Fermi is sure that he's right, he says, Jesus, you have to publish this. You don't understand what you've done. He says, no, it's too easy, it's trivial. These morons don't understand it, okay? So Fermi doesn't know what to do, you know, but okay, in a week or two, he's going to a meeting. He's going to talk about some work. He says, look what I'll do. I'll just announce that you've done that. You don't publish it. Let me just tell the world that you've done it. A day after, he says, look, I got an idea, okay? I'll invent the name of some old Roman professor, and they say that, you know, this guy invented this, the world should know. He won't hear of that, Majorana. And you can't do that, that's Majorana's work. 2 years later, as you know, Chadwick finds Majorana, finds neutron, comment to Majorana. You see, he says to Fermi, you don't have to publish. You just give these morons a little time, they realize it on their own. Well, physics, you know, the whole thing of doing physics is making sure that you beat the other guy. You know, that's what we are trying to do anyway. For a while, Majorana stops even coming to this group. He's from a rich family, he can live on his own, he doesn't need money. He's isolated for years. And one day he says to Fermi, I'd like to come back to physics, I would like to get a job. So, there was a job in Napoli. The year is 36, 37. And he has no papers, he's basically published nothing, but he's very influential, Fermi at the time. He makes sure that Majorana can get a job called on a direct glory or special merit, whatever, under the condition that he writes a paper. He takes this out of a drawer, okay? This is what changed particle physics or neutrino physics, if you wish, forever. And this is the now central aspect of modern neutrino physics. This paper was in the drawer. He was never going to publish it, but thank God he did. According to which, you know, neutrino could be a Majorana particle. Now, I wish I could say the rest is history, but we still don't know. 1937, okay? What we are saying that in this picture, it's sort of coming out naturally the neutrinos and Majorana particle. Because of, if you like to introduce a right-handed neutrino, okay, which you may not, we just noticed that we got a Majorana master. This is not an exact statement, notice, because go to the other limit when MUR is very small. What will happen? In the limit when this go to 0, you would only have a Dirac mass. So strictly speaking, you don't know, because if this is very small, as unnatural it may be. I'm only saying it's natural in this picture. Then I would introduce a state, which is mu L plus C mu L bar transpose. So I want to remind you that the name left or right is not a good name. This is left-handed, sorry, this is right-handed, this is left-handed. There is both left and right inside. Just keep that in mind. The thing is that the neutrino, once again, when it interacts with the electron, picks up this component. But if the guy is not wild spinner, if it is massive, it's going to have both components. Massive particles have both components. In the case of Dirac, they are independent, UL and UR. In the case of Majorana, they're just complex conjugate of each other. So this guy is called the right-handed neutrino, and it's really not neither right-handed nor neutrino. The name is misleading because you should keep in mind, and I'll show you immediately why that's important. And this is called the left-handed neutrino. Neutrino means a light, small neutron light. This guy is supposed to be very heavy.
Why we don't introduce a Majorana master for the left-handed?
Well, we did at the end, but we couldn't write it down. This was the point of the last lecture. This breaks the standard model symmetry.
But why not we put it like explicit in the...
Because I cannot break. Because this is the whole point of everything that I said from the beginning, unfortunately. The standard model as it is a good theory of electroweak phenomena under the condition that there is no explicit breaking. That destroys everything because the theory wouldn't be renormalizable, okay? Explicit breaking took us to propagators which had wrong high energy behavior. With a little thought, you can show that no other explicit breaking is allowed, okay? That's, of course, is a serious task in field theory. But we had this agreement, remember, I'm not going to go back on that, you and I, that we allow only spontaneous symmetry breaking in order for the theory to be renormalizable. That has been proven by Hoft and the others. Therefore, this starts to be 0. This is the standard model prediction, based on the gauge symmetry as we do for Q1. But, okay, the thing that you notice, and this is important for the homework to understand why I gave you the homework that I gave you, that because of the non-trivial mass matrix, these particles they are eigenstates under Lorentz symmetry. They are okay as states, physical states, okay, they transform correctly. The thing is that they are not eigenstates of this, right? Nu and N mix. This is not nu. The eigenstates here, this heavy guy would be N plus epsilon nu. And the light guy would be nu minus epsilon N. You see immediately. Right, from here, this mass matrix M, when it acts on epsilon 1, will give me M Dirac, and this would be Mn. Agree? Plus, okay, let's be a little more careful, plus epsilon M Dirac. So this is Mn. I take out, I ignore this, this is small. What remains here, epsilon 1, under the condition that epsilon is m Dirac over Mn. So they mix a little bit. For most of the time, I'm going to ignore the mixing. But it's not irrelevant, because imagine that somehow you produce this N. Remember, you start with an interaction which was UL gamma mu, EL W mu plus. This guy is a mixture of heavy and light states, if you wish, and vice versa, right? There will be, what will come in will be epsilon NL gamma mu EL W mu plus. Because nu mixes with N. I'm keeping the notation of nu N. This is not a correct notation, but I don't want us to get lost. Okay, I want you just to keep in mind that there is a mixing. I should introduce heavy and light notation, but it will be hard to live with that. I keep calling this guy neutrino, but it's not an eigenstate of the mass matrix. Okay, this mixing is tiny, so most of the time I'm going to ignore it. And this is, you see, what will be interesting, what you will find out, that if I produced N, I could identify it because it's going to decay immediately into the electron and W boson. And more to it, okay? Now we should be a little more systematic about the Majorana nature of this guy. Before I end up being more systematic, let me just summarize it here. If you wish, the correct statements would be, well, just write it one. That, we'll keep it here, that nu, or the light state, let's put a bracket here, is nu minus epsilon and the heavy state. So in other words, nu is not, nu is what? Is the light state plus epsilon heavy. Okay? Agree? Mm-hmm. Therefore, from this interaction, I produce this interaction. And I will give up on writing this heavy and light, okay? I'm going to call this guy N, and I will remember that it mixes with that it has a new interaction with the W boson. In other words, through the, I'm sorry, I shouldn't have erased it, the neutrino mass matrix, let's keep it here all the time, M Dirac, Mn. Simply tells me, okay, that these particles I call nu N, they, through M Dirac, produce this mixing, and by that mixing they produce a new interaction. I have to worry how to produce this guy, okay, but once I produce it, there will be an interesting signal to look for, okay, interesting detail to look for, okay. Now, this was one way of reasoning. Remember I said, so what we learned, there was the first thing, that if there is a right-handed neutrino, we are taking what we call, this is a seesaw picture, according to which neutrino is Majorana, due to this heavy guy. Now you say, I don't like this picture, okay, you're not convincing me by introducing it. Then I say there is another way of reasoning, due to Weinberg. It's really more or less at the same time when the seesaw picture was emerging. Weinberg says, okay, but says, imagine the picture in which there are no new light states in the standard model. So, okay, so imagine the standard model has only neutrino and electron light states. Of course, other generations like this, we can copy generation by generation, but no new states. Okay? In other words, there is no light nu R. Okay, you can think of Weinberg as a situation in which nu R is very heavy, it's not accessible, okay? Says, I don't care what it is, Weinberg says. What is the new physics behind it? Weinberg says, look what has to happen. If I write a mass term for a neutrino, the only way to write it, okay, that you realized yourselves, was to introduce twice the Higgs field. This is the quantum numbers of SU2 cross U1 teach me that. So it had to be cut off by some new scale, which I call lambda Weinberg. Let's use the blackboard bed. So in other words, you prove immediately that M neutrino would be written as V squared, the vacuum expectation value of this guy, over lambda W. You agree? It has to, and it has to be Majorana, because if there are no new states, it has to be Majorana. Of course, that means that there is new physics beyond the standard model, okay? Just the same way that the Fermi effective interaction tells you that there is new physics beyond the electromagnetic interactions. And how would you get new physics? By integrating out, by having heavy fields that are so heavy that they actually do not propagate at low energies, right? How did we get Fermi interaction, remember? G Fermi, how did we get this interaction? Well, we found out we can exchange a heavy particle, which propagator q squared minus mw squared gave us. So it's so heavy that it doesn't move, okay, at low energies, okay. So this is Weinberg generic operator. It has to have this form. Notice you say, okay, if he's right, then this should give us the same form. But notice that this is Yukawa Dirac square V0 square over Mn up to sign. So if you wish M new absolute value, which is Yukawa Dirac square over Mn, V square has Weinberg's form, as long as 1 over lambda W is Yukawa Dirac square over Mn. Okay? So even if you don't like this particular seesaw mechanism, but as long as you believe that there is some physics that once you integrate it out, okay, then now how would you understand this particular expression, which is sort of Weinbergesque from the effective interaction point of view? You see, what would you have to produce? Remember that my Majorana mass is of the form nu transpose C nu, which what I mean roughly is nu, twice neutrino enters, right? So in other words, neutrino has to enter, neutrino can become a right-handed neutrino. Here, this is the Higgs field. This is how we would draw it, you agree? Well, phi, sorry, there will be an interaction, let me not put the web. This will be the Higgs field. No, neutral component here, which becomes nu R. Then what I did, I said that I'm allowed to write here a Majorana mass term. What effectively it means, when I go to the vacuum, this will produce nu phi 0 square. And I will have the propagator, which is 1 over k slash minus mn. But if mn is heavy, okay, the same reasoning as Fermi. A heavy particle integrating out, what we say, is sort of bidding this guy to propagate. You say it's so heavy that kinetic energy can be ignored. Then you immediately produce the Weinberg operator. Was that clear? You see, if we want to talk about neutrino mass, you and I, we are taking beyond the standard model, necessarily. So I, in particular, have been arguing now for many years that this is our best window. And I will argue this with anybody, okay? This is the only place when the standard model failed. We can speak of other issues that you and I try to understand, but this is where it failed, and you should attack the theory that fails where it's vulnerable. Okay? So in other words, if I want to understand neutrino mass, I'm forced to do either an effective picture. And by the way, yesterday or Monday, someone noticed that if I wanted to write this neutrino mass, which has T3 half and half, which is 1, that meant I had to put a triplet here. And this is what I did, by the way, because out of 2 doublets I created a triplet. This has a half, this has a half, I created a triplet. Remember? So for example, you say, well, I don't like your seesaw mechanism, okay? I don't like your Weinberg operator. I, for example, will introduce a triplet new scalar and give it a small vacuum expectation value. You can do that. It's actually a popular model that people have been studying for quite a while. And you once again, you will get a Majorana mass. So it goes into the category, okay, I'm trying you, even if you do that, you will end up with a Majorana mass, okay? I want to convince you that this now should be taken seriously. That neutrino is a Majorana state. So almost any which way we look at it, that's to indicate that. And the thing that you could play with, actually I think I'll suggest you this as a homework problem. You and I would have to show that this vacuum expectation value of the triplet is actually end up being V squared over mass of that triplet. But that will be another story which is not important now. Okay. All I want to say is that no matter how I look at it, and this is quite natural because at the end there is this mystery. Neutrino and electron which live in the same multiplet live in such a way that mu is less than 1 million times m electron. And that's very puzzling. And what is the difference between neutrino and the electron?
The charge.
The charge. They are exactly the same. You see, if for double boson that's one and the same particle, double boson doesn't give a damn whether you call it neutrino or an electron. So is the charge. But what is the difference when you speak is the charge? Well, neutral particle can have Majorana masses. And you see this idea of Majorana, which then is explicit in seesaw or this Weinberg, whatever, is making use of that. This is what enables you to have a tiny neutrino mass, because notice that, imagine that m Dirac is equal to me. You say, I want to live in the world, which actually I don't have to assume that Dirac is small compared to the electron. Then I predict that Mn equal me squared over m nu. What did we conclude? Someone remembers? I forget. Well, I can put in a GeV again. This was 10 to the minus 3. Square is 10 to the minus 6. GeV squared. And this I should take less than the electron volt. So it should be bigger. No, this is bigger than 10 to the minus 9 GeV. So this is what? 10 to the 3 GeV. Which kind of fits what I wanted to argue here. That this right-handed guy having nothing to do with the physics of the standard model would be natural to live above the scale of the weak interactions. Okay. So even if you look at it this way, it's kind of happening. Okay. The number of these statements beyond the standard model is not the thing that you have to really learn now. All I want you to learn when the dust settles, you know, what it boils to, if we are right that neutrino is Majorana, that just you understand how to work with Majorana states. Okay. And if neutrino is Majorana, so in other words, we take the Majorana picture seriously, Majorana neutrino mass. We have a way of depicting it. We usually see what is the neutrino. We want to emphasize that neutrino, in the case of Majorana, is entering on both sides, and usually neutrino Majorana mass is depicted like this. If you think about it, almost as if these guys are annihilating into nothing, you know, through neutrino mass. And this is why, of course, we have a violation of the lepton number. Lepton number entering, lepton number entering. This is lepton number 2 violating quantity. And therefore you say, aha, therefore you say, okay, I believe that there'll be delta equal to physical process. And immediately after, 6 months later, Racca, and then a year later, Furi, maybe in a clearer manner. So this is 1938. Just want to emphasize how long a time it has been. We've been searching for this. It's 1938. The way it goes, it's going to be a century. I hope it's going to be done before. And what's the process? So I can so the summary was, remember, one was seesaw, Majorana, neutrino. The other was effective operator, which had dimension 5. We just told me that there was new physics. Again, I concluded the same. The third was, okay, I want to be another model, I want to, a triplet Higgs. Okay, this is why I took you to this picture, and therefore the process that has become celebrated by now, that violates lepton number by 2 unit, it's so-called neutrinoless double beta decay. 2 neutrons enter. And notice the way it works. The Majorana mass term, of course, if there is this one, there's going to be the opposite one. Nu going out, right? Because we write it nu L transpose C nu L plus Hermitian conjugate. And Majorana, Hermitian conjugate will be nu L dagger, C dagger, nu L star. In this case, 2 neutrinos entering. In this case, the neutrino leaving out. And therefore it means that this can go through a Majorana neutrino mass. Do you agree? Nu L. The breaking of lepton number is happening on the line of
question.
Yes, please.
What happens with the energy? Where does the energy go?
Which energy?
Of the neutrino. I mean, what happens with the conservation of energy?
Where?
In the
I have 2 neutrons. 2 neutrons are heavier than protons. And they produce 2 two electrons, energy is conserved.
And the energy carried by the neutrinos?
But when
They are of shell.
when electrons scatter in QED, where does the energy go? Well, the only thing that you know that this energy, actually, energy momentum, is conserved. These guys, of course, carry what we call virtual energy. They are not on shell. This is very important. Okay? And now that you ask, neutrino is not on shell. And if you wanted to sort of estimate this, how would you estimate and how it would go? Okay, we should be a little more careful here. How would you and I estimate? Well, you would say, okay, I don't know, it's some complicated nuclear physics, okay, but how do I estimate the strength of this weak part? Well, you would say, here I have a propagator 1 over mw squared, you agree? Then another 1 over mw squared. And there is G, 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 G. So there is G squared, G squared. By the way, this we call GF squared together, right? And then there will be a propagator of neutrino. But it will have to go through a mu. The way I depicted it, it's highly suggestive. We are going to show that in a second. This is just estimating, divided by P square of neutrino. Okay. It's off shell, of course. And the nuclear aspect of physics is measured by the off-shellness of neutrino. You know, I don't know how much it is off-shell. People tell me, people that do this in typical large nuclei that study this, okay, that this is of the order P of neutrino here, P of shell. Let me just call it P. This is particle which is not on shell, okay. The P is of the order of 100 MeV, quite big. Someone has to tell you that, okay, of shells. The rest you will figure out, okay. So this is one particular way that people parameterize this, and then when they measure this and put the limits on the lifetime, they put the limits on mu from there. But how do we really get mu? This is only picturesque, what I drew. It all has to come from here, from the weak Lagrangian. Nu L bar, gamma mu, E L, W mu plus. So I would have to follow this line, but you know, when we follow the line, remember what we argued, you know, it's a very, we don't work like this. We don't say electron, electron. I don't write E bar, E bar. Okay, how do we deal with these processes? We say electron going out is equivalent to positron entering, right? So, and here there is, of course, Hermitian conjugate. So, what does it mean in practice? Remember, I raised it, but I maybe shouldn't have. That, well, once again, so we don't need to. That I can work with psi L or which was equivalent to psi L bar was psi C R transpose C. Am I right? And psi L is C psi C R bar transpose. This is the same relation. This is the antiparticle of psi left, and psi left is the antiparticle of its own antiparticle, okay? I don't know what is first, you know, can or neck. You see how we have this convention? I normally write the electron here because I'm used to working with an electron or the positron, but I can rewrite it just to see what happens, okay? So if I rewrite it, how will it look like? This will be G square root of 2. What will be nu L bar? Where am I? This will be here. We actually did it before in the mass matrix. So this would be nu C R bar, nu C R transpose C gamma mu. What would this be? EL would be C E C R bar transpose. Thank you. Okay. I need you awake. There is Commission conjugate. I know. Well, I'm just writing one piece, okay? Which is, what is this?
Star
Gamma mu transpose. Should be with the minus sign, I think. I always forget it. Okay, plus or minus sign. Up to a sign. It's minus gamma mu transpose. Okay, if it's minus gamma mu transpose, that's what I like. Then this is G over square root of 2. So I'm going to take a transpose of this equation, and I'm going to get ECR bar, gamma mu. It becomes a transpose of gamma mu transpose, minus sign because they anti-commute, and then nu CR. So what, and this is very important, okay, the case of neutrino may not be so spectacular, but the case of particle N, which we have to discuss in the homework. The same thing you would write with the N guy. This is not an important thing, comment to make. What I keep saying, electron entering is equivalent to positron going out. Electron going out will be equivalent to the Risk-Commission conjugate, which is EL bar, gamma mu, nu L, W mu minus, right? Which will be nu CR bar, gamma mu ECR. Let's write in its full glory. It's useful. So all when I say, look, I mean, this is not to say it explicitly. When we speak particles and antiparticles, it's just safe to remember it's the spinner and charge conjugate spinner. So electron going out is equivalent to positron coming in. And this is how we work. So look, let's show it. Okay, this was an estimation. In other words, what I will do here would be electron, left-handed electron going out, that is E gamma mu L, you agree? There was G to the fourth, 4 G's, E L coming out, gamma mu L. Then I write the propagator of neutrino, which is, we call it P slash plus mu. Remember what we said? First homework, that Majorana Lagrangian end up looking the same as Dirac. The propagator is the same. The Majorana Lagrangian goes I psi bar, gamma mu d mu psi, Majorana, minus m Majorana, psi m bar psi m. It's very innocent looking. It looks the same way. It's dangerous to think like that, but it's useful for calculations because inside there is a particle and antiparticle, okay? And that will always lead to some physics, that there is a question in the homework. I don't know if you had a look. When there is this decay, I'm asking you if that's the only decay. And you will see why I said it. So I have P square minus m nu square. The same propagator, okay? That's what I've told you. And then, what is happening here, I have to look at this Lagrangian. I have to look at this. ECR, you see the crux of the issue, okay, the crux of the issue, which I forgot completely, okay. That this is in general electron entering, positron going out, neutrino entering, leaving, antineutrino entering. But in the case of Majorana, this is the same particle. In the case of Majorana, nu is nu L plus C nu R bar transpose. Should have written this. Therefore, this was very important. This sort of weak interaction can be written, this is it, can be rewritten also as G over square root of 2 And the first piece would be ECR bar, gamma mu. No, it may confuse you. I will write it EC bar, gamma mu, R nu. This is the same neutrino in the case of Majorana. There is no distinction between U and UC. This, what I wrote up to here, was just notation. Here is the physics. Nu C is equal nu. So, maybe I could have just written nu R. So that you get used to it. This is not the right-handed neutrino. This is the left-handed neutrino. You understand? There is no left-handed neutrino. If it's a Majorana, it's both left-handed and right-handed. It's both neutrino and anti-neutrino. The guy's crazy, completely. Doesn't know what to, what to be. Thank you. We have to remember that, okay? I'll tell you there is a catch here. A very, very important question in the homework that leads to an interest in physics at LHC. Plus the opposite thing would be nu R bar, gamma mu, ECR. Of course, EC is EC, W mu plus, W mu minus. You see, for the electron, of course, I will never confuse EC with the electron, okay, because the guy carries opposite charge. That's the reason why positron is different from the electron, just because they have different charges. According to Mr. Majorana, when they are neutron, they could be, and we are showing that they actually naturally end up being one and the same particle. The neutrino. Okay. So please, this is neutrino. And this is why I changed the notation to nu R, which seems like some nu R guy. I call it N. Okay. You can't get confused. So this is my neutrino propagator, and here I should have an interaction which is gamma nu R EC. Notice the interaction becomes right-handed. Okay. In other words, when we say that weak interactions are left-handed, it is a convention. They are not left-handed. When there is left, there is right, if you wish. Okay? It just means that electron and neutrino is left-handed, but the positron and neutrino becomes right-handed. If neutrino is Majorana, because otherwise this would be a different particle. Okay, I'm now going to pretend that neutrino is a Majorana particle. I'm going to take it seriously to see where it's going to take us. And now notice, there were also, I will just write mw to the fourth. Gamma mu and gamma nu will get attached to mu nu here, okay. To,
What the photon probability?
sorry?
Photon probability.
Photon. W.
Yes.
Right, they will attach. Well, we can work in the, it doesn't matter where we work, we are at low energies, right? So the propagator is G mu nu. So this becomes, it's attached to the, in other words, there is a vertex here. There is also P bar, gamma nu n, P bar, gamma mu n. Twice. Well, when I write P, it's actually up quark and down quark. Just let's keep the notation that the nuclear physicists would use. Notice what I was claiming, that I expected, because of the schematic way of me understanding the Majorana mass, that this will go through the mass. And notice when L goes through P slash becomes R, here becomes L, so this dies. Only a mu contributes, you see it. L goes through a mu, here becomes R, and R squared is R. So this is equal to G squared, G to the fourth, over MW to the fourth, mu over P squared. Mu is tiny. And then there is E bar, gamma mu, gamma nu REC. P bar gamma nu, actually here would be left-handed, let's write N P bar, share with gamma mu Ln. Notice by the sheer analogy what I've written here. In the homework you have interaction which is epsilon because of the missing NL bar gamma mu EL W mu plus. This is equal. There is G also, but anyway, proportional to. This is proportional to a ECR bar gamma mu NCR W mu plus. That's Hermitian conjugate. So the Hermitian conjugate is NCR bar gamma mu ECR W mu minus. Just like neutrino, okay? I'm just repeating the same thing neutrino. When N couples to electron and a W, remember N is Majorana, therefore this is N again. Okay, all I'm saying that Majorana, when I say that there is a Majorana spinner which was nu L, say, CL plus C L bar transpose, or right plus, because this is right-handed, okay, this is equivalent of saying that CM is CMC. After all, this takes you by charge conjugation to another. Okay. So whenever you might run a particle, when you see NC, just remember this is N, okay? And it's a side comment for the homework. There ought to be light on the blackboard, don't you feel that? Okay, you're saying that it's not good for recording. But there is less visibility because of the lack of light of the blackboard, no? It doesn't bug you. Okay, you see better than me, obviously.
You are young.
Yeah, well, I'm not going to argue with that. It's implying something about me. You didn't say it, but well, you can see as you get older that the notion of young keeps changing. I'll see you in 10 years, hopefully. Then we can talk again. So, the thing is that this all makes sense. Okay, well, first, okay, at least you've learned that if neutrinos are Majorana particle, you and I may observe neutrinos double beta day one of these days. Okay, everybody's looking for it all over the world, and in particular there are experiments, very interesting experiments in the Apennine Mountains of Italy, the Gran Sasso Mountains, okay, which is the highest peak, Corno Grande, big horn. So the Gran Sasso Laboratori Nazionali, National Laboratory of Gran Sasso, okay, there are experiments, in particular very beautiful experiments that are looking for that. What they will have to see in the conservation energy that you ask now, that there is now a peak. The sum of the electron energies is not going to have a distribution. It's going to be the opposite from neutron decay, right? The discovery of neutrino. This is now anti-discovery of neutrino. We want anti-discovery. We want to make sure that it's not there. Okay, the other thing when this is 0 no 2 beta, the 2 beta itself has been observed, and the lifetime is about 10 to the 21 years. This is what simultaneously decay. This was suggested in 1935 by Maria Geppert-Mayer, and as you can see that they raised it a couple of years later, 37, 38, okay, people came up immediately with this process. In this case, the only thing that we have, the lifetime, is now getting to about 10 to the 25 years. Unfortunately, no, this equivalently implies that mu Majorana mass, this doesn't put a limit on neutrino mass, because sometimes people get confused by that, only on the Majorana mass. It's less than about electron volt. Actually, they cited it below. But let me keep it conservatively around the electron volt. I'm not an expert on nuclear physics, and I can't speak of any authority why some people claim it's 0.6. Okay, it sounds miraculous, but people have done this calculation in various groups, and they keep now converging more and more. It's coming to that point, you know, when there was the beautiful thing that we've learned about the solar neutrino puzzle. When people started to notice that there was a puzzle, there was a question, well, do you understand the sun? The same question, you know, you talk about a complicated process, do you understand the nucleus? And he started with one guy in Princeton, Bacall. I don't know if Smirnov talked about it, it's a mind-boggling thing. He spent his life on this. In the end, the bottom line is we understand what is happening with the sun, okay, with a good precision, okay. A great work came out of that, which now confirms everything that we know, except that neutrinos can oscillate inside the sun, but anyway. So now, and then various other groups picked up and they started to converge more and more. Similar thing is happening here now. The numbers are becoming better and better as we go along, not just from the experiment, but from the thing is, okay, so we see one day, suppose you and I see the neutrino as double beta decay, so we'll know the neutrino is Majorana, apparently. True? This is what a typical conference talk says often. Well, not a true expert, okay. Wrong. This is just one possible source to this process. What if there is some new physics that leads to the same process? You see, it's similar to the thing. You will see that when you study grand unification, when you put quarks and lepton together, you won't be surprised that you get proton lifetime, proton decay. If I put quark and lepton together, someone is going to transform quark into a lepton. When I put two leptons together, you see, one day I put lepton, neutrino, and electron. Imagine that I did it before they saw weak interaction. I said, look at the beauty putting them together. But of course, what is neutrino? That doesn't make sense to speak like that, because in order to speak of neutrino, there was a weak interaction, so forget it. But you say, well, okay. Anyway, you would, if for some reason they were together, you will learn that there is someone will transform nu, and we call that guy W, and you know there will be weak interaction. If I put them together, just by putting them together, I didn't observe anything. I'm saying quark will become lepton eventually. Proton is going to decay into, I don't know, pi 0 plus positron. What do I know? Whatever. I open a Pandora box, anything can happen. So there are often people that say, oh, imagine this proton decay, that will be a proof of grand unification. Okay, that's of course crazy. When you see proton decay, the only thing that you will see is proton decay. You will never know what caused it. This is the problem of low energy physics. You cannot know what caused it. Okay, that's very different from the colliders. The reason that we particle physicists use colliders the way a shoemaker uses a hammer, because we have to see what is going on, and the only way to see it is by identifying the physical process, okay, the culprit. In other words, I have to see that someone is producing a W. You know, this is very different from actually producing, let's say, a W boson or a Z boson, even more spectacularly, right, E bar, and then finding its decay rates. It's not that you are seeing here and then this case into Q bar, nu bar, and so on, okay? You actually see the Z boson, you see the peak. You can study the properties of that peak, you can measure the spin, you can measure the decay width, you've seen in the particle data group. That means seeing, okay? So therefore this is not true. Even this ingenious statement, okay, or innocent statement is wrong, okay? It will be exciting, it will be beautiful, because it will be a violation of what appears is a law of nature. It will tell us that the standard model is not the whole story. Whatever the explanation is, the standard model must be modified. Even if neutrino causes it, you cannot write the Majorana mass term in the standard model. Therefore, 0 nu2 beta means that there is physics beyond standard model. But I can't know what it is by seeing a phenomenon. So we took one example. So we're going to say a little more. Especially after you do the homework, I'll say even more, because I want you to see something. Maybe you will notice something interesting in the problem. We said, suppose then, in this most natural scenario, which these days is becoming canonical, this is becoming the picture of neutrino mass C, so there should exist a new heavy neutral lepton. How would I know that it exists? Well, it's coupled to it's coupled through the Dirac mass. There is a coupling nu and Higgs. M Dirac over MW, you agree? You agree? Just like the, is this clear, please? Just a few more minutes. When I wrote Yukawa Dirac, I wrote it V over square root of 2, something like this. There was a term nu L nu R, but this is nu N. Remember, there is always accompanying it 1 plus H over V. Then we stopped writing, but we remember that, because in the unitary gauge they go together, H plus V. Did anybody did the SU5? When you handed it in, I didn't look at it. I was too busy. Did anybody hand in SU5?
I tried.
But if you wrote it down, okay. Then, so, are you still trying? You want to keep trying, because I could send you a solution, okay? But I don't want to do that if you're going to keep working, okay? Because I have a next problem which is very interesting, okay? For those, okay, I will send the next problem for those of you that, because it's really beautiful, and I'll send you the paper that deals with it. It's hard. Anyway, you will notice there in SU5 that the singlet that goes in the direction, you will find the usual thing, okay? When there is a wave, there is a guy that is along the wave. And that guy will have the usual Higgs mass and so on. This is always true. And this gives me this. This is M Dirac. So Yukawa Dirac over square root of 2 is M Dirac over V. And that was G over 2, M Dirac over MW. Because MW, if you remember, is G over 2V. With my conventions of the vacuum potential value, so on and so forth, okay? So this is always, a Dirac mass term is always of the form. Therefore, we know that if these guys were lighter than the Higgs would decay. There's a new channel. I just opened a new channel, okay? Imagine that the guy is lighter than the Higgs. The trouble is that this is small. We decided that M Dirac was of the order of M electron. Actually, it has to be smaller because I'm taking it lighter than the Higgs. So you can imagine this is another invisible. There is an invisible channel, basically, right? With the branching ratio of less than the electron, 10 to the minus 10. We won't see the Higgs decaying into an electron at the LHC. It's too small. The Yukawa couplings, okay? So I'm saying that there is this guy, and I try to argue that it's more likely that the guy is heavier than the Higgs. So I need to produce it. Well, I could produce it through this interaction. I could first produce the Higgs. That's hopeless, you agree? I'm not going to achieve this. By then having a tiny coupling of order 10 to the minus 5 or less. Okay, so forget it. So what I could do, there was an interaction G over square root of 2 epsilon n bar gamma mu E W symbolically. Let me just write n bar E W. So if I produce a W, and I produce them copiously, I'm going to produce n. The trouble is that m epsilon, again, is m Dirac over mn. So in other words, the cross-section for producing n will be proportional to m Dirac over mn squared. But notice what is m Dirac over mn squared. That's m nu over mn. And this is less than 1 electron volt, we argued, and this is bigger than 10 to the 3 GeV. This is obviously hopeless, right? Imagine producing a TeV particle. If you want to produce a TeV particle at LHC, whatever you like to imagine, you better couple with the strength of order 1. Like the W boson. Okay, this is a good coupling. This is of order 1. This is the same reason, by the way, that we couldn't even imagine producing the Higgs in the past. Ever directly. That's the problem with the Higgs. It couples very weakly with the fermions, therefore you can't produce it. We ended up deciding that we will produce it, you knew, through the gluon fusion. Okay, it's crazy, through some 2 gluons. Okay, we have to, we'll spend a couple of lectures on the Higgs in detail. Very soon, I'll clean a little bit neutrino picture. Since you finished the homework on the Higgs decays, we can talk more seriously. So somehow, I think that you and I should feel unhappy about this picture. That I have a phantom particle that explains the smallest neutrino mass, but I cannot see it. So, it looks neat, it works, whatever. But the physicist should not accept that. If it doesn't bug you, then I don't know, the next lecture may not be so illuminating. I'll go on and try to give one more lecture on how you could have new physics where n could be produced, or analogous states. If you like the Higgs triplet, we can talk about that too. And try to think whether a machine like LHC or the next collider, hopefully to be built in China, as they keep telling us. Nobody else has money, you know, the global crisis left us in a situation with having no next machine. This is very bad. We'll try to see whether there is a natural candidate that would let us produce n. And then you and I think how you would identify it, and whether we could really disentangle the seesaw mechanism. Okay, if I want to have the theory claiming of explaining the mass, in this case a neutrino, I should be able then to check every step in that process. Okay, enough for today. Any public questions or? Okay, so that's it for today. We are free.
It's correct.
Oh.